Assalamualaikum and hi again everyone. In this session I will share with you the topic on estimating an unknown population variance denoted by sigma squared, and I will also share with you the estimation of an unknown population standard deviation denoted by sigma. As you know, sigma is simply the square root of the population variance sigma squared. Are you ready to join me? Let's go. Similar to the previous sessions on mu and pi, let us look at the learning objectives of this topic first. At the end of this session, you should be able to achieve the following three learning objectives. First, you should be able to obtain a point estimate of an unknown population variance sigma squared and for an unknown population standard deviation sigma, either by identifying or recognizing the value of the point estimate from sample information or by calculating the value of the point estimate using your scientific calculator if you are given a set of sample data. Second, at the end of this session, you should be able to construct a confidence interval for sigma squared and sigma. And finally, you should be able to also interpret the constructed confidence interval for sigma squared and sigma. In this slide, we will look at the point estimates for two unknown population parameters denoted by sigma squared and sigma. What is the point estimate for an unknown population variance denoted by sigma squared? What is the point estimate for an unknown population standard deviation denoted by sigma? These are two questions that we want to address in this slide. The answer to these questions is rather straightforward. The point estimate for sigma squared is the sample variance denoted by S squared, whereas the point estimate for sigma is the sample standard deviation denoted by S. If you are given a set of sample data, the two values S squared and S can be calculated using any scientific calculator. The skill of using the calculator to find the values of S squared and S has been covered in detail in Chapter 1. You may recall the skill and do practice it again for this topic. However, if you have sample information provided in a question, you should be able to recognize the values of the point estimates directly from the sample information. Now, look at example 3.5 in page 74 of the textbook entitled Statistics for Engineers. Let us read the question. A study on an operating system for a portable computer has been carried out thoroughly to estimate the variance of response time. A random sample of 10 portable computers are chosen and give a standard deviation value of 8 milliseconds. Assume that the response time follows a normal distribution. Two questions that we want to solve in this slide are: first, what is the point estimate for the true population variance of the response time? And second, what is the point estimate for the true population standard deviation of the response time? This is an example where you can identify or recognize the point estimate value from the sample information directly. Here in this question, the sample information provided includes the sample size n equals to 10 and the standard deviation as equal to 8. So for question 1, the answer is simply the sample variance S squared, which is equal to 64 milliseconds squared. Here, sigma cap squared indicates an estimate of sigma squared, which is simply the S squared, whereas the unit of variance must also be squared. Next, for question 2, the answer is the sample standard deviation S, which is equal to 8 milliseconds. As mentioned before, this value can be recognized directly from the sample information. Let us now look at how we are going to construct a confidence interval for the unknown population parameters sigma squared and sigma. You may refer to pages 73 and 74 of the textbook for further information. To construct the confidence interval for sigma squared, first, we may use the following statistic. Chi squared equals to n minus 1 s squared divided by sigma squared, which is distributed with a chi-square distribution with the degrees of freedom nu equals to the sample size n minus 1. Note that the chi-squared values are non-negative and its distribution is rightly skewed. Obviously, the chi-squared distribution is not symmetric like Z or T distribution. Now this formula, chi-squared equals to n minus 1 s squared divided by sigma squared, is available in the stat table and formula booklet, page 3. You may want to browse the table and locate this formula in the table. Let sigma squared be our parameter of interest this time. Rearrange this formula. We will then get the following expression. Sigma squared equals to n minus 1 s squared divided by chi squared. By borrowing this formula, then, we can construct the confidence interval for sigma squared, which will be further explained in the following slide. From the previous slide, we knew that sigma squared equals to n minus 1 s squared divided by chi squared. By borrowing this formula, we can then construct a confidence interval for the unknown population variance sigma squared. Here, the 100 times 1 minus alpha % confidence interval for the unknown population variance sigma squared is given by this expression. The lower limit is n minus 1 times s squared divided by chi squared alpha over 2 nu, and the upper limit is n minus 1 times s squared divided by chi squared 1 minus alpha over 2 nu. Notice that the modification we did here relates to the chi squared. Previously, chi squared was the statistics or random variable from the formula directly given in the table. Now in the confidence interval formula, we modify this as values of chi squared. In the lower limit, we use the value of chi squared at alpha over 2 nu, whereas the value of chi squared we use in the upper limit is chi squared 1 minus alpha over 2 nu. It is important to note that the degrees of freedom nu is the sample size n minus 1. The values of chi squared alpha nu can be obtained from table 6 in pages 36 to 37 of the statistical table and formula booklet. The values of chi squared alpha nu are always non-negative, therefore we should not use a plus-minus sign in constructing the confidence interval for the variance. And finally, we only have one case when we want to construct the confidence interval for the population variance, that is to use chi squared. An alternative expression for 100 times 1 minus alpha % confidence interval for the unknown population variance sigma squared is as follows. We can write like this, where the inequalities are written in the formula with sigma squared notation is in the middle. As we know, the confidence interval is actually derived from the probability, and for this confidence interval, we can also say that the probability that the interval n minus 1 s squared divided by chi squared alpha over 2 nu and n minus 1 s squared divided by chi squared 1 minus alpha over 2 nu may contain the true population variance value sigma squared is 1 minus alpha. What do you think the confidence interval for the unknown population standard deviation sigma would be? Do you have any clue? Yes, you're right. To construct the confidence interval for the population standard deviation sigma, what we can do is to square root the final answers that we obtain for the confidence interval for a population variance sigma squared. Here, the 100 times 1 minus alpha % confidence interval for a population standard deviation sigma is given by this expression. The lower limit is the square root of n minus 1 times I squared divided by chi squared alpha over 2 nu, and the upper limit is the square root of n minus 1 I squared divided by chi squared 1 minus alpha over 2 nu. Before we look further at a number of examples on constructing the confidence interval for sigma squared and sigma, let us be familiar first with the table of chi squared alpha nu values. Please refer to Table 6, pages 36 and 37 in the Statistical Table booklet. First, how do you find the value of chi squared 0.0510? Here, what you need to do first is to look at the chosen alpha equals to 0.05, listed in page 36. Once you get to the column of alpha equals to 0.05, go down until you get to nu equals to 10. Do you notice that the value of chi squared 0.0510 is 18.3070? Good. What about the next value? What is chi squared 0.9510? Here, you need to do first to search for alpha equals to 0.95. That is in page 37. Once you get to the column of alpha equals to 0.95, go down until you get to nu equals to 10. So the value of chi squared 0.9510 is 3.9403. Do you get the value? Well done. You can also check that chi squared 0.02521 is 35.4789 and chi squared 0.97521 is 10.2829. Can you follow so far? Great! Notice that for the same degrees of freedom nu, chi squared alpha nu is always larger than the chi squared 1 minus alpha nu. That is to say, chi squared alpha nu is farther away from 0 as compared to chi squared 1 minus alpha nu, which is much closer to 0. For example, chi squared 0.0510 is larger than chi squared 0.9510. Here we consider alpha equals to 0.05, so 0.95 is simply 1 minus 0.05. Similarly, you can observe that chi squared 0.02521 is larger than chi squared 0.97521. Here the alpha is 0.025 and 1 minus alpha is 0.975. Why do you think this happens? It's simply because the chi squared alpha nu value is determined in the table such that the probability of chi squared being at least chi squared alpha nu is alpha, where alpha is shown as the red shaded region The larger the alpha value, the closer the chi-squared alpha nu is to 0. On the other hand, the smaller the alpha value, it implies that the chi-squared alpha nu will be shifted farther away from 0. Let us now look at an example on constructing the confidence interval for the population variance sigma squared and for the population standard deviation sigma. Example 3.5 in page 74 is revisited. Remember, we have used this example to find the point estimate for sigma squared and sigma. Now we are interested to find the solutions for the following two questions. First, construct a 95% confidence interval on the true population variance of the response time. And second, construct a 95% confidence interval on the true population standard deviation of the response time. From the sample information, we know that the sample size n is 10 and the sample standard deviation is 8. From the sample information, we may use this information to answer the question. From both questions, our focus is to construct a confidence interval, and the parameters of interest are sigma squared and sigma respectively. Before we answer the question in example 3.5, let us look at the following 4 steps. First, recognize the information given in the question. As noted earlier, the sample size n is 10 and the sample standard deviation is 8 milliseconds. Next, identify the parameter of interest that we want to estimate. In this case, we are interested in constructing the confidence interval for the population variance sigma squared and the population standard deviation sigma, which are both unknown. In the third step, choose the appropriate case if relevant. And we know we only have one case in constructing the confidence interval for sigma squared and sigma, that is to use chi-squared in the formula. Substituting all the values required in the formula, then we can solve the question. Therefore, the answer to the first question is given as follows. A 95% confidence interval for the true population variance of response time is n-1 s squared divided by chi-squared 0.0259 and n-1 s squared divided by chi-squared 0.9759. Here, alpha is 5% or 0.05 as we construct a 95% confidence interval for sigma squared. Thus, alpha over 2 is 0.025 and 1 minus alpha over 2 is 0.975, whereas the degrees of freedom nu is n-1 equal to 10 minus 1, which is 9. The value of chi-squared 0.0259 is 19.023, which can be obtained from table 6, page 36. whereas the value of chi-squared 0.9759 is 2.7, which can be obtained from the same table 6 but in page 37. Substituting all the values required in the formula, we can then get the answer for a 95% confidence interval for the true population variance of response time given by 30.279 and 213.333 milliseconds squared. Hence, we can then construct a 95% confidence interval for the true standard deviation of the response time sigma by taking the square root of the values in the 95% confidence interval for sigma squared. That is to say that the 95% confidence interval for sigma is the square root of 30.279 and the square root of 213.333. So the 95% confidence interval for the population standard deviation of the response time is 5.503 and 14.606 milliseconds. Looking at another example on constructing the confidence interval for sigma squared and sigma, we may refer to task 3.10 in page 74. A random sample of 13 bolts is selected and the inside diameter is measured. The sample standard deviation of the bolt inside diameter is 0.018 mm. Assuming that the inside diameter of the bolt is normally distributed, construct a 90% confidence interval for the true standard deviation of the bolt inside diameter. Before answering this question, remember the 4 steps. First, recognize the information provided in the question. We can notice that we have a sample size n equals to 13 and the sample standard deviation s equal to 0.018 mm. So write this information using the correct notation. Next, identify the parameter of interest we want to estimate. In this question, the parameter of interest is obviously sigma, which is the true standard deviation of the bolt inside diameter. Next, choose the appropriate case if relevant. As we know, we only have one case in constructing the confidence interval for sigma squared or sigma, which involve using chi-squared in the formula. We do not use Z or T in constructing the confidence interval for sigma squared or sigma. And finally, by substituting all the required values in the confidence interval formula, we can then solve the question. The solution to this task question is given in the next slide. Having identified all the information required to solve this task 3.10, we can now solve the question. As we know, a 90% confidence interval for the true population standard deviation of the bolt inside diameter, denoted by sigma, is the square root of n-1 s squared divided by chi-squared 0.0512 and the square root of n-1 s squared divided by chi-squared 0.9512. Hope you already noticed that alpha is 10% or 0.1, so that alpha over 2 is 0.05 and 1 minus alpha over 2 is 0.95. Please do not forget the square root, because we aim to find the confidence interval for sigma in this question, not sigma squared only. Therefore, please do not forget the square root. We already knew that n is 13 and s is 0.018. Whereas the values of chi-squared 0.0512 and chi-squared 0.9512 can be obtained from table 6. Can you check the values of chi-squared 0.0512 and chi-squared 0.9512 from table 6? What do you get? Do you get chi-squared 0.0512 equal to 21.0261? What about chi-squared 0.9512? Do you get 5.2260? If you do, bravo guys! Having all the required values substituted in the formula, we then have the 90% confidence interval for the true standard deviation of bulb inside diameter given by 0.0136 and 0.0273 millimeters. Notice that the lower limit is lower than the upper limit. If we look again at task 3.10, suppose we have this extra question. What is your interpretation on the obtained or constructed 90% confidence interval for the true standard deviation of the bulb inside diameter? Two possible answers to this question are, first, you may say that the probability that the interval 0.0136 and 0.0273 may contain the true sigma value is 0.9. Remember, sigma value is fixed, although we do not know its true value. It is wrong to say that the probability that sigma lies within 0.0136 and 0.0273 is 0.9. Instead, you should say that the probability that the interval 0.0136 and 0.0273 contain the true sigma value is 0.9. Another more popular way to interpret the confidence interval is to say that we are 90% confident, or we have a 90% degrees of confidence that the interval 0.0136 and 0.0273 may contain the true standard deviation value of the bulb inside diameter. Again, it is wrong to say that we are 90% confident that the true standard deviation value lies in the interval 0.0136 and 0.0273. You should rather stress that the interpretation of the confidence interval refer to saying that we are 90% confident that the interval 0.0136 and 0.0273 may contain the true standard deviation value. Before we end the session on this topic on estimating the unknown population variance and standard deviation from a single population, let us check the attainment of this topic 3 learning objectives that I have highlighted at the beginning of this session. Are you now able to obtain a point estimate for sigma squared and sigma? You should already know by now that the point estimate for sigma squared is the sample variance S squared, and the point estimate for sigma is the sample standard deviation S. Please make sure you know how to obtain the S and S squared values from your scientific calculator if you are given a set of sample data. However, for some questions that provide sample information, you should be able to recognize the point estimate values directly from this sample information. What about the attainment of the second objective? Are you now able to construct a confidence interval for sigma squared and sigma? Remember, we only have one case which involves using chi-squared values in constructing the confidence interval for sigma squared and sigma. You may use exactly the same confidence interval formula for both sigma squared and sigma, but do not forget the square root when you are to construct the confidence interval for sigma. And finally, are you able to interpret the confidence interval for sigma squared and sigma that you already constructed earlier? You may repeat watching this video to ensure that you fully achieve all these 3 learning objectives of the topic. Please try solving more questions on this topic, especially from those that are available in the textbook Chapter 3 exercise and Supplementary Exercise 3 to strengthen your knowledge and understanding on this topic. If you have any question related to this topic, please do not hesitate to contact me personally, either via email or WhatsApp. Until then, thank you very much for watching this video. Wassalamualaikum warahmatullah and enjoy your online learning experience.